Okay, next we have 11.7, which is finding maximum and minimum values, which again, you can kind of relate it to what you did in Calc 1 with, if you remember, taking the derivative, finding your critical numbers, and then using the second derivative test to figure out if it was a max or a min. Okay, so again, 3D surfaces also have local and absolute extrema, just like 2D surfaces do. Okay, and it's the same definition as 2D. Local maxima are higher than points around it. Local minima, obviously, are lower than all the points around it. Okay, and then we can have absolute maxima. Absolute maxima are higher than all other points on the function. And absolute minima are lower. Okay. Just like in 2D, a critical point occurs when your derivative is 0. So what does that mean in 3D? Your partial in respect to x at that point is 0, and your partial with respect to y at that point is 0. Really, any directional derivative is 0. Once you have shown that 2 of them are 0, you're good. But these are obviously the easier ones to find. Okay, and that's what we're going to use. So 0 or doesn't exist too. Okay, and then you have a tangent plane. Z equals Z naught, so whatever f of AB is. Okay, rather than a tangent line. All right. So it would be a horizontal plane. There's a tangent plane, it's horizontal. Okay, so let's get an example. These can get kind of fun. I kind of like doing these. Let's see. Let's get some more colors here. All right, so an example. We have the surface. Okay, and I, again, strongly encourage you to go to a 3D plotter and plot that surface and take a look at it. See what's going on there. Okay, and we want to find your, I think this one is just asking for, is it just asking for the critical points? Yeah, I think it's just the critical points. I think maybe we'll go back to it later. So find your critical points. Okay, so our solution here. Our partial at x, so treating y as a constant. We got a product rule going on here, right? First times the derivative of the second plus the second times the derivative of the first. So we'd have negative xy plus y minus xy minus y squared. So negative 2xy plus y minus y squared. Okay. And then our partial at y is going to be similar. And kind of like we said before, I can see how x and y are used in the same way as in the equation. So I can really just switch them out in the partial derivative there. And I wouldn't be able to do that if like one of those was being squared, or in the parentheses if it was y plus x minus y, or 1 plus x minus y. But since they are very much interchangeable, I can switch my x's and my y's and have the same thing. Then my partial in y will be 2xy plus x minus x squared. And I don't have to go through that work, okay, as long as I can justify that. All right. So first we can see, when does our partial at x equal 0? Okay, so when does negative 2xy plus y minus y squared equal 0? So we can actually do some factoring here. Let's get a y out of there. Let's see, so y would be negative 2x plus 1 minus y. Okay, so that will equal 0 if y is 0. Or, and it doesn't matter what you want to solve for here, it's easier to solve for y if y equals 1 minus 2x. Okay, so those, it doesn't have to be a specific value. It can be in terms of the other variable. So in those two cases, my partial at x would be 0. So now I'm going to check and see if they also make my partial at y 0. In fact, I should actually make sure that I check for anything that would make the partial at y 0. So, but I'm going to just plug those in first. Okay, so my partial at y, when, oops, what am I doing here? Oh, I'm sorry. Okay, so my partial at y, back up a second, is negative 2xy plus y minus y squared. If y were 0, whoops, I threw myself off again. I got to get it together here. These should be x's. Okay, so plugging y equals 0 into that, so something like this, we'd have 0 plus x minus x squared. Okay, that would be 0. Let's factor out an x, 1 minus x. If x were 0 or x were 1. Okay, so there's one critical point. So when y is 0 and x is 0, that makes both the partials equal to 0. When x is 1 and y is 0, that would also make both of the partials 0. Okay, and if you can double check just by plugging those in. Then we need to take a look at our 1 minus 2x. Okay, so we're going to evaluate our partial at y equals 1 minus 2x. Okay, so then we would have negative 2x times 1 minus 2x plus x minus x squared. See how that's much easier to solve that if you sub in for y than it is for x. Otherwise, you can rearrange it and do it the other way if it would have been easier the other way. This would be negative 2x plus 4x squared plus x minus x squared. So we'll have negative x squared. I'm sorry. Let's combine that with the 4, right? We'll have 3x squared minus x, and set that equal to 0. So that'd be if x is 0 or x is 1/3. Okay, and remember y was 1 minus 2x. So if x is 0, then y is 1. Okay, in this case here, if x is 1/3, then y is 1 minus 2/3, which is 1/3. Okay, so we have only one additional critical point here because we've already taken care, oh no, we didn't. I was looking up, we had 1, 0, we don't have 0, 1. So 0, 1 is another critical point, and so is 1/3, 1/3. Okay, so again, if I took these 4 critical points, I'm going to copy the other ones over. If I plug those into both of my partials, I would get 0. Okay, so those are all critical points. So that's the first thing that we need to do, is establish where the critical points are. Now we need to test if they're maxes or mins. Okay, so that's, if you remember in Calc 1, the next step was your second derivative test. Okay, and if the second derivative was less than 0, that means that it was concave down like that, and so then you had a max. If your second derivative was greater than 0, that means it was concave up and you had a min. Okay, and if it were 0, then you had an inflection point, remember? Okay, something like that. Okay, in 3D, these are going to be similar. I'm going to have a really hard time drawing them. Your max would kind of be like, a hill in your surface that you can kind of see in all directions there. Okay, your min obviously will be like a divot in your surface. You can kind of see in all directions. Instead of what we call an inflection point, we have what's called a saddle point. So if you can picture what a saddle looks like, boy, I'm going to try to draw it. A horse saddle looks like this, right? Where it's going up in this direction, but down over the horse in that direction. Okay, a lot of kids say it's like a Pringle, if you can think about that. But just imagine, like, if you're standing here, if you look to the left and the right, it would go down. If you're looking straight ahead and straight back, it's going up. That's a saddle point. Okay. So what we do is we have what's called, we just call it D. Okay, your book does, which is D at AB is your second partial at X at AB times your second partial at Y of Y at AB minus fxy AB squared. Okay. In other courses, we look at this as kind of a matrix and a determinant of your matrix, or we would have, it's called a Hessian. And your Hessian is set up like this. Okay, and the determinant, we might even call it H, the determinant of your Hessian, then it's fxx times fyy minus fxy fyx, which is the same as, just remember, fxy and fyx are the same thing. Okay, so I think that's easier to remember than it is, the formula that your book gives you, just because the way that Hessian is organized, it's really easy to remember. It's just kind of like coordinates. And then your determinant, if you remember, it's AB minus CD, right? The determinant of a 2 by 2 is AD minus BC, where you'd have A, B, C, D. Okay. But this is going to be important for you to remember however you can. Okay. If D is greater than 0 and your second partial is greater than 0, and we say X, but it doesn't matter if it were Y, or they're both going to be greater than 0, right? If D is greater than 0, this second piece here can only be positive or 0. So that means that this first part has to be greater than 0, which means they both have to have the same sign, okay? Then you have a local min. Okay, so you can think of it as being like, if this is true, it's like it's concave up, okay? If D is less than 0, I'm sorry, D is greater than 0 again. And your partials there, again, they'd have to be the same sign. So if they're both negative, okay, then you can think about it being the concave down and you have a local max. Okay, otherwise, here, if D is less than 0, it doesn't matter. Those two things would have to be opposite signs in order for that to happen, because again, the second piece can only be positive, so it's less than 0. We know that those two double partials there, fxx and fyy, are different signs. Then we have a saddle point. Okay, and then if D equals 0, it is inconclusive. We don't know what's going on. Okay. All right, so we're going to go back to our previous example where we found our points. Okay, so back up to here. All right, with this function. I'll rewrite it down here. Okay, so back to our example where we had f of xy was xy times 1 minus x minus y. Your partial, there was negative 2xy plus y minus y squared. And then for y, it was negative 2xy plus x minus x squared. And then if you remember, we had our critical points at 1, 0, 0, 0, 0, 1, and 1/3, 1/3. Okay, so we're going to use our Hessian, the determinant of our Hessian there, to figure that out. So keep moving here. Second partial with respect to x, we'd have negative 2y. That's it. Second partial with respect to y would be negative 2x. Okay, and then fxy or fyx, remember they should be the same. With respect to y, we'd have negative 2x plus 1 minus 2y. Okay, if we take the y partial and then derive it with respect to x, we'd also have negative 2y plus 1 minus 2x. So those are equivalent. Okay. So next thing we would do is we're going to do this determinant of the Hessian here, but we can plug in the numbers right away because we know we're not going to come up with like a big long expression for this. You could be asked to, where you'd have to do D is negative 2y times negative 2x minus 2x plus 1 minus 2y. I don't know why I did a square bracket squared and expanded out, but you don't have to. So I guess we can leave it like that. I just kind of made a list usually. So like at 0, let's do 1, 0. Fxx would be 0. Fyy would be negative 2. Fxy would be, let's see here, negative 2 plus 1, so it'd be negative 1. Okay, so D, again, would be the first 2 minus the last 1 squared. So 0 times negative 2 would be 0 minus 1, so it's negative 1. Okay, so that means that we have a saddle point. Since D is less than 1, or less than 0. And we can also, the next step too would be to complete the point. So it would be x is 1, y is 0, and then going back to our original expression, if x is 1 and y is 0, it's 0, right? Okay. So we have a saddle point at 1, 0, 0. Okay, next one we're going to look at is 0, 0. So fxx there would be 0, fyy there would be 0, fxy would be 1. Okay, so d, again, that would be 0 times 0 minus 1 squared. So it's negative 1. Since d is less than 0, we have a saddle point at 0, 0. Back to your original expression, if I plug those in for x and y, I would get 0. Okay, next one, we're going to have 0, 1. So fxx would be negative 2. fyy would be 0. fxy would be negative 1. Okay, and your determinant there then. Again, it would be negative 2 times 0 minus negative 1 squared. So it's negative 1, which is less than 0. Another saddle point. And it would be at 0, 1, 0 if you plugged it back in. Okay, last one then, we've got 1/3, 1/3. It's a little bit trickier to work with, right? Fxx would be negative 2/3. Fyy would be negative 2/3. Fxy, let's see, we'd have negative 2/3 plus 1 minus 2/3. Okay, so negative 4/3 plus 1, so we'd have negative 1/3. Go back there. D then would be negative 2/3 times negative 2/3 minus negative 1/3 squared. So we'll have 4/9 minus 1/9, which is 3/9, which is 1/3. So now D is greater than 0, and our partials or less than 0, so that's going to be a local max. At 1/3, 1/3, if we plug it back into our equation, let's go all the way up again. Okay, if we have 1/3 times 1/3 times 1 minus 1/3 minus 1/3, then we have 1/3 times 1/3 times 1/3, which is 1/27. There we go. Okay. So again, I would definitely graph that function on a 3D plotter, plot those 3 points on there, and take a look at them. Okay. All right. Last thing that we need to do is talk about, we have absolute extrema also. So if you remember from Calc 1, check your endpoints, right? Okay. Because you could have something like on your interval, it's a terrible drawing, but I was trying to show that you could be higher at the endpoints and have a local max in between them. Okay, so we could do something like that, where there we have a local min, there we have a local max, but neither of them are absolute, right? You had to check your endpoints. In Calc 3, check your boundaries. Boundaries, good to have boundaries. You need to check them. Okay. So let's do an example of that. Okay. I'm going to go through one big long example here. So this might take a little while. I'm going to pick a good color. So our example, we're going to have F, and you're like, well, what are the boundaries? They have to give them to you. So we've got this surface bounded by the triangle with vertices 0, 0, 0, 2, and 4, 0. Okay, so what that means is, see if I can do a decent drawing here. I'm going to do it to the side. Okay, we have some sort of surface going on, you know, and maybe it's got some highs and lows in it, some peaks and valleys there. That's the best I can do, guys. Okay, if I had more time. All right, so, but we only care about the piece that's above like a triangle there. So we only care about, you know, maybe a portion of this, okay? Which means maxes, we can have your local max and mins or saddle points in the middle of that region somewhere. But along the edges, we could also have some absolute extrema, okay? So we're gonna go through the steps here that we did before. So our first step is to find our partials. So we'd have 1 minus y for x, and then for y, we'd have 1 minus x. That makes it pretty easy. Okay, these are only going to both be 0 if x is 1 and y is 1. And also, so if x is 1 and y is 1, then we have 1 in our function, f of 1, 1 would be 1 plus 1 minus 1, so 1. Okay, so critical point there. Now, is that within our bounded area? Let's take a 2D view at our bounded area. Actually, let's kind of draw this out a little bit. So that triangle that bounds us, 0, 0, 0, 2, and 4, 0. Oh, that's 3, Mrs. Wera, not 4. Let's extend that a little bit. There we go. Okay, so our boundary there, there, there. Okay, so then our critical point at 1, 1, 1 is definitely in the region. Okay, so we've got a critical point there, so we could have a max, min, or saddle point going on there, but then we could also have it happening in any of those boundaries. Okay, so we got to check them. We'll finish up our 1, 1, 1 there. Okay, so fxx would be 0. Fyy would be 0. Fxy would be -1. Okay, so here, don't forget D is fxx times fyy minus fxy squared. So it's -1. Okay, so since D is less than 0, we have a saddle point. So it's not going to be an absolute max or min. Saddle points don't do that. Okay. So now what we do is we check along our boundaries, and it might sound intimidating, but it's really not. You just kind of take one dimension out of your boundary and just treat it as well, not necessarily a line, but treat it. It'll be a function in one variable. So along the y-axis. Okay, if we are on that boundary that's along the y-axis, then x is 0. Okay, so f of 0 y would be y. Okay, so all we need to think about is that function y. Okay, so f prime at 0y, or along 0y, would just be 1. Okay, we have an increasing function. Just go back to your basic derivatives here. We took the derivative and it's 1. It means it's always increasing. As y increases, this function is increasing, which means we could potentially have a min at 0, 0, or a max at 0, 2, right? Here I'm going to do 0, 0. If I put it into the function, it'd be 0. Over here, I'd have 0, 2. Let me put it into the function. If x is 0 and y is 2, then I have 2. Okay, and that lines up with exactly, the slope is 1, right? I mean, just think about that. If we're at 0, 0, and we're increasing at a rate of 1, then we go to 0, 2, we're at 2 for our z-value. Okay, and then over here, once we get to this one, we'll have 4, 0, 4. Okay, so we want to check both of our endpoints. Okay, 0, 0, 0 could potentially be a min, and 0, 2, 2 could potentially be a max. And we don't have to worry about any other point along that boundary. Okay, now we're going to take a look at the x-axis. So on the x-axis, y would always be 0. So f of x 0 would just be x. Our derivative there is 1. So we're also another increasing function. Okay. Again, you guys, I can't stress it enough. Put this in a 3D plotter and look at what's going on along that x-axis. Okay. So we have an increasing function along the x-axis. Okay. So again, 0, 0, 0 is a potential min. 4, 0, 4 is a potential max. And in fact, we can see then 0, 2, 2 is not going to be an absolute max because we're already higher than it at 4. Okay. We don't have to rule that out yet, but that's, we can see that potentially our absolute min is 0 and potentially our absolute max is 4. Okay. Now that other boundary, it's going to get a little trickier, but not much. Okay. We need to know what that boundary is. So this would be y equals mx. Oops. It's a line. The slope is not 2. The intercept is 2. Y equals negative 1/2 x plus 2. That's just the equation for that line. I can look at it. I can see the slope is negative 1/2. The y-intercept is 2. Okay. So along y equals negative 1/2 x plus 2. So we're going to have f of x negative 1/2 x plus 2. Okay, so we need to plug that into our original equation, which was x plus y minus xy. Okay, so we're going to have x minus 1/2 x plus 2 plus x squared over 2 minus 2x. So we've got x squared over 2 minus 2x plus 1x. So just minus x minus 1/2 x, so minus 3/2 x. Okay, so that's what's happening along this boundary. Okay, it's kind of like a parabolic form there. All right, if I look at that, it's a parabola that opens up. So it's kind of high up here, it dips down, and then it goes back up. Okay, if you were to look at it in 3D, we would see that along this boundary, it's kind of looking like that. Okay, whereas along the x-axis, it was what? It was increasing and also increasing along the y-axis, and then it kind of takes that parabolic dip there. Okay, we'll try to, if you guys remind me, we'll plot this one in class too, but otherwise definitely try it yourself. Okay, so our derivative there would be, let's see, x, okay, minus 3/2. So again, we would want to check the endpoints, okay, which we already did. So we would want to look at, in this case, 0, 2, 2, 4, 0, 4, but we already have them. But again, those are the endpoints of the boundary. And then also, we have a critical value when x is 3/2. So 3/2, okay, and then y. Remember, along the boundary, y is negative 1/2 x plus 2. So y is negative 1/2 times 3/2 plus 2. So negative 3/4 plus 2. So that's going to be 5/4. Okay, now f of 3/2 5/4, okay, would be x plus y minus x y. So 3/2 plus 5/4 minus 15/8. So then we have 6/4. Oh, I need eighths, don't I? I'm just gonna, we have 12/8 plus 10/8 minus 15/8. Okay, so 22 minus 15, so we have 7/8. Okay, so now all of our points. Okay, so we're going to make a nice list here. So first we found 1, 1, 1, which was a saddle point. So it's not any sort of absolute extrema. Okay, then we did 0, 2, 2, 0, 0, 0, and 4, 0, 4, right? And then I'm just cross-checking my list here. Yeah, the last one. Then we had 3/2, 5/4, and 7/8. Okay, so there is our min, absolute min, and here's our max. I don't know why I made the arrows going the other way. Okay, but your absolute, remember, you always report the value. So absolute minimum value of the function is 0. Your absolute maximum value is 4. And we could say where they occur. So your absolute minimum value of 0 occurs when x is 0 and y is 0. Your absolute maximum value is 4, and that occurs when x is 4 and y is 0. Okay, but oftentimes, most of the time, they're asking for the value of the function, which means the dependent variable. Okay, so that's a lot of fun. You get to go through all of that. That was one problem, guys. Okay, I think I have time to do one more kind of difficult example if you want to keep paying attention here. This one gets pretty mathy too. If you want, this would be a good chance to kind of pause and maybe do a couple practice problems from the classwork and make sure you're understanding it. And maybe come back here once you get to the more difficult problems. But we're going to have another example here. Find the maximum volume. I spelled volume wrong. Of, try something here. A rectangular box that. Oh, I'm sorry. Chromebook issues again. Shocking, right? I'll do this. It's getting kind of hot, so I'm wondering if that's why it's freezing up. Is inscribed, I think that might be it, in a sphere of radius r. That's a spicy meatball. That's a lot going on there. Okay, so think about that. We're going to put a rectangular box in a sphere. Okay, you probably, I would hope, at this point in your life, you have the intuition to imagine what that's going to be. I think we can all kind of figure that out, or if it's not coming right to your mind, maybe think about it a little bit, you'll get it. But we got to show it mathematically, right? There's no fun if we can just picture it. So we're going to go ahead. This is an optimization problem, basically. And when we get to section 11.8, we're going to do a slightly different way of doing these optimization problems. But volume is length times width times height. Okay. And when you think about this, well, here, let me get this. X squared plus y squared plus z squared equals r squared would be the sphere. Okay, so if we were to graph this, obviously the easiest place to put our sphere is centered at the origin. Okay, and think about the corner of the box that would be like in the first quadrant. All right, so, oh my goodness, it is. Okay, so let's say that the corner of your box would have the coordinates x, y, z. Okay, it doesn't really matter if it's in the first quadrant. Okay, so obviously your box is going to be centered around the origin also. So volume, the length of the box would be 2x, right? Because you got to think about going into the other quadrants also. The width would be 2y, sorry, and the height would be 2z. So it'd be 8x, y, z. So now we're working with 4 variables instead of 8. Okay. So this can also be described as 8xy times the square root of actually I guess we were down to 8 variables. Okay, so 8xy times the square root of r squared minus x squared minus y squared. So we just eliminated another variable. Okay. So we're going to find max and mins of this, right? Take a look at what we got here. Okay. We have your x's and y's in there. R would be a constant. So we're going to try to maximize the volume. Okay. So your next step is to find your partial with respect to x. So we would have first, actually I'm going to take the 8y out because that'd be a constant. So first times the derivative of the second. Okay, oops. Starting to freeze up. Okay, come on. All right, plus the second times the derivative of the first, which would just be 1. Okay. So we'd have, let's see. I'm going to distribute my 8y. The 2's can cancel out. So it'd be 8x squared y, and it'd be a negative over the square root of r squared minus x squared minus y squared plus 8y times the square root of r squared minus x squared minus y squared. Okay, because remember we have to figure out when this is going to equal 0, right? There's a lot going on there, but we're going to get it simplified. The next thing we can do is, let's clear some fractions here, right? If we multiply everything by that square root over the square root, okay, so then we're going to have negative 8x squared y. Oh, I'm sorry. We're just going to multiply the second one by that because that's going to give us a common denominator. Okay, and then we're going to factor, there's a lot of different things we can do here, but I think that the next easiest thing is to factor out an 8y. We have negative x squared minus x squared. Oops, I missed my minus y, or plus here. I think I did this in a different order than I really wanted to, but that's okay. And I factor out an 8y from the entire top. Okay, so that leaves me with negative x squared plus r squared minus x squared minus y squared over that square root. So then I have 8y times r squared minus 2x squared minus y squared, all over the square root of r squared minus x squared minus y squared. And again, this is another one where x and y are treated similarly, or exactly the same in the equation. So I know that when I find my partial with y, I could just switch my x's and y's. It's a nice shortcut. Okay, so now we can figure out what's going to make it 0. Okay, the first obvious thing would be if y is 0 and x is 0. Everything is 0. Okay, you'd have the point 0, 0, and then, well, z squared would equal, z squared would equal r squared, right? I guess if we go back to our function, if x were 0, y were 0, it doesn't even matter what z would be. Your volume would be 0. That's your min. Okay, so x, y, we don't want that. Some math teachers would call that's a trivial solution. Okay, that's the one that we don't want. We want the ones that actually make it 0. So, and it would be, and not make the whole function 0. So if we could have two things happen here. If r squared freezing up again. Okay. It's a good time to switch a color anyways. Okay, so if r squared minus 2x squared minus y squared were 0, okay, and r squared minus 2y squared minus x squared were also 0. Okay, that's what we want, right? It doesn't make any sense. This is an application problem, right? It doesn't make any sense for x or y to be 0. Okay, so we're not even concerned at all about any combination that involves x or y to be 0. That's not going to maximize the volume of a box. Okay, so we want to solve this system, and we're going to do it by substitution. So we could do here, let's see. Oh, I'm sorry. We want, well, you know what? I did it a different way in my notes. I'll I'm gonna do it this way though. Okay, in my notes I left that 8x in one of them. It doesn't matter because you get two solutions. We don't care about one of them. Okay, so again, if we do substitution, let's see here. Let's do r squared equals 2x squared plus y squared. Okay, so then we're going to sub it into the other one. So 2x squared plus y squared. And some of these get really tricky. It's just like there's not a specific method to use. Okay, so there might be more than one way that you guys can think of to do these, and that's great. There's no step-by-step that I can give you. It's just, here's a system, solve it. Okay, and what we're trying to solve for are x and y. So, okay. So we'd have x squared minus y squared equals 0, which would mean x squared equals y squared. Okay, which means x, positive or negative x equals positive or negative y. And again, we were talking about that intuition at the beginning. Hopefully most of you caught on to the fact that it would have to be a cube, so where x would equal y. Okay, which means any combinations, positive x would equal negative y, any of that. Okay, so if x equals y, okay, then what we can do here is go back to this. If x equals y, then r squared equals 2x squared plus x squared. R squared would equal 3x squared. So x squared would equal r squared over 3. So x would equal the square root of r squared over 3, which would be r over the square root of 3. Okay. And again, go ahead and make them positive or negative. It doesn't matter. Okay. And again, think about the application here. We're going to have a lot of x values. Okay. Because it's all the vertices of your cube. That's where they would all be. The goal here is to find the volume of the box. Okay. So we just need to know that this is half of one side, r over the square root of 3. Okay. X equals y, so y would be r over the square root of 3. Okay. Going back to our volume equation, here's the volume of the box. Okay. So eight xy times the square root of r squared minus x squared minus y squared. You could also figure out what z is. Again, more than one way to do this. So 8 times r over the square root of 3 times r over the square root of 3 times the square root of r squared minus r squared over 3 minus r squared over 3. So we'd have 8 times r over the square root of 3 times r over the square root of 3. Let's see, that's going to be times the square root of r squared over 3, right? So we're going to have 8 r over the square root of 3 cubed. So 8 r cubed over 3 root 3. That's your final answer there. Okay. So again, you guys go through this. It's a lot of work. It's a tough problem, but try to kind of think logically through this a little bit here, okay, about how some of the shortcuts that we might have taken made sense. Y, x, y, and z were all the same dimension. You know, it's a cube. Cube fits in a sphere. And that's, some of these examples get kind of tough at the end, but do your best, and we'll go through as many as we can together. So, done.